Very good afternoon to the audience and the speakers of this session on city gas distribution. City gas distribution is perhaps more difficult than laying the cross-country trunk pipelines. So it is going to be an interesting session. I will invite the speakers one by one, and each speaker will be given a time slot of 15 minutes. So I request each one of you to limit your presentation within the time limit. So without taking any further time, I will request Mr. Rajiv Ek, who is from GAIL India Limited. He will be speaking about crossing of 4 rivers through micro tunneling in natural gas pipeline. Over to Mr. Rajiv.
Thank you so much, Shastri sir. Very good afternoon to one and all present in this meeting room. As the topic suggests, it's a pipeline project. It's a Baroni-Guwahati 720 kilometer pipeline. It covers almost 3 states, starting from Bihar and entering West Bengal and then to Assam. So this pipeline is very important from the point of view of Northeast, because with the commissioning of this pipeline, the Northeast gas grid is now connected with the national gas grid. It is a wonderful thing, and as per Government of India's vision to increase the use of natural gas from 6% to 15%, this pipeline plays an important role, especially for the Northeast region. So you can see this pipeline crosses through a chicken neck in West Bengal. You will be very surprised to see why it is chicken neck. You see in the diagram in West Bengal, one side of the map, you will see Nepal and other part is Bangladesh. So our pipeline passes only 500 meters away from the Bangladesh border. And this chicken neck is very narrow. Already IOCL, NRL, Oil India, they have laid pipelines. So we have faced a lot of resistances because the space available is very less. So we'll come to the main topic. What is microtunneling? Why we have adopted microtunneling? Why not open cut? Why not HDD? You know all, there are 3 typical crossing methodology. One is open cut, another is HDD, and third one is microtunneling. Of course, there are so many conventional methods are there, but we will be talking about microtunneling in this presentation and why you have not adopted the technology HDD. This is the microtunneling in BGPL project. You can see there are 6 sections. So if you start from Bihar, first section is section 1, then is section 2. In section 3, there is a river, name is Tista River. This river originates from Sikkim, from the state of Sikkim, and you don't have any control over this river. You will see that there is no rainfall in West Bengal. All of a sudden, there are a lot of water flowing through this river. And this river ultimately flows to the Bangladesh. Now, next river is Raidak River. That is also in Bangladesh. This river originates from Bhutan, and its length is initially it was a 360 meter. But during actual execution, we have seen that there is a erosion in river bank. So we have to increase the length of the microtunneling to 460 meters. Next comes Sankos River. This river also originates from Bhutan, and its length is 760 meters. And the last one, it is very interesting, Kanamakra River in Chirang district in Assam. We have crossed this pipeline by microtunneling. So these are the 4 rivers, 3 in West Bengal and 1 in Assam. We have crossed through microtunneling process. Now the question comes, why microtunneling? Why not open cut? The question naturally comes into mind. Why microtunneling? If you go for open cut, you have to go for an excavation of 7 to 8 meters from the existing bed level. It's a very difficult job. And you have a very limited working window, 6 to 7 months in a year. So you have to complete everything, all activities during this period only. And construction of coffer dam and diverting huge quantity of water because the water table in the river is very high. And as a result, you have to cover a depth of water of 4 meter, 5 meter, 6 meter, depends on the season as well as water flow in the river. And width of the river will be more than 500 meter during dry season only. Dewatering during excavation is very difficult. You have to put lot of pumps. Working window available is very less, 6 to 7 months. Sometimes in Tista River, we have seen the working window available was 5 months only. So in view of all these difficulties, we have decided not to cross the pipeline by open cut method. This is the main basic. And why it is not open cut? Because if you start open cut, the established bank of the river, you have to restore the bank. And government of West Bengal is very instrumental that you have, if you want to restore the bank of the river, you have to give it job to the government of West Bengal. So it is very difficult because your timeline will be very tough. Now comes the horizontal directional digging. If you do horizontal directional digging as per the clause of the tender, the scout depth of the river in most of the cases is 2.5 meter, and you have to go minimum depth of 5 meter below the lowest grade level. So once the drill bit started traveling, it has to come across various boulders and pebbles in the route, and as a result, there is a chance of frack out, which is very dangerous for the environment. So the probability of using HDD for this particular depth is not possible. At this depth, there is a chance of frack out. In case of HDD at a higher depth, then you have to, as per soil strata, as per geotechnical survey report, it shows that there are boulders and pebbles along the entire width of the river. That's why we have decided not to go for HDD. The rivers in West Bengal, same average, it's not moving. Oh, so now the rivers in Kanamakra River in Assam, same condition happens in Kanamakra River also. We have avoided the open cut method because you have to excavate for a greater depth of 7 to 8 meter, and Kefardem construction is very difficult. You have to dewater the water, and the depth of the water will be almost 3, 4, 5 meters, as well as the width of water flow is 400, 300, 250 meters based on the season of the season. Cutting and restoration of the river bank is also difficult. Working window available is very less. And similarly, HDD in the same line, whatever we did in West Bengal are the same. Microtunneling, what is microtunneling? Microtunneling is nothing but a pitch launch technology. If you compare with HDD, it's a surface launch technology. In this method, you have to construct a shaft of desired depth as per design given by the designer, and you have to construct a shaft, and in the shaft, you have to put the microtunneling boring machine along with a power pack and with the jacking frame and thrust wall. And once the microtunneling boring machine is operated from an operator which is separated from the river bank, and it is a separate control room, the operator is operating the microtunneling boring machine. Once the microtunneling boring machine moves forward, and jacking pipe is inserted inside the tunnel, and this system keeps on going until and unless it reaches the receiving shaft. I will cover the what is launching shaft, what is receiving shaft. I will next slide. So these are the components of a microtunneling machine. The most important is launching, intermediate, and receiving shaft. Then microtunneling boring machine with a power pack, control container. The operator is able to control the speed of the microtunneling machine based on the soil strata. If the soil contains more boulders and pebbles, then the speed of the machine reduces and the efficiency of the machine also comes down. Then jacking pipes, this is very important. The tunnels are consist of, once the microtunneling machines enters the earth, just behind the microtunneling machines, we are putting jacking pipes. These jacking pipes are of 2.5 meter, almost 5 tons of weight, and the size of the machine is 1,200 mm, For Tista River in West Bengal, all the rivers, we have used the microtunneling machines of 1200 avian make. The reason is that initially when we started microtunneling in Tista River, that time it was not known that what will be the outcome of this microtunneling, because first time in Gale we have done the microtunneling. In microtunneling Tista River, 1024 meter is the length, that 1200 millimeter AXN DN 1200 meter model is used, and we have made 4 shafts. Shaft 1, shaft A, shaft B, and shaft C. From drive shaft 2 to shaft B, 350 meter, shaft B to shaft A, 320 meter, and shaft 1 to shaft 350 is 350 meter. And Kanamakra River, whatever mistake we did in Tista River, we have encountered, we have corrected in Kanamakra River in Assam. Here we have done one best thing by putting 3 shafts instead of 4 shafts, because construction of shafts takes a lot of time. That's why we have used a higher capacity machine of 1600 avian make, which has the capacity to straightway drill maximum more than 600 meter in one go. So we have taken this model. Here, that's why you can see there are 3 shafts only. One is the launching shaft, then receiving shaft, and another is the receiving shaft. Microtunneling mobilization. Construction of approach road is very difficult. You can see in the picture, throughout the season, some amount of water is flowing in the river. That's why we are facing a lot of issues. So band formation is required, continuous dewatering is also required, and the sinking of the shaft is important. Otherwise, once the sinking is very slow, then you cannot construct the shaft. The bottom plugging is very important. So these are the issues we faced during microtunneling. And after construction of shaft, installation of jacking frame at the launching shaft, then lowering of MTTV along with the power unit, installation of power cables, hydraulic hoses, bentonite slurry system, connection of all units to the control container, commencement of boring by MTTV machine. The MTTV advances forward, as I already mentioned. Once this MTTV forwarded, we used to insert one jacking pipe. Once the jacking pipe entered distance, we put one more jacking pipe. This system continues till the microturning boring machine reaches the receiving shaft. Pipe string created, the important thing is that the size of the shaft is 7 meter. So you have to go for preparing the string of 1200 meter, 1031 meter based on the length. So we have to hydrotest it, first welded, then hydrotested. Then again you have to cut into small pieces of 6 meter, because the diameter of the shaft is 7 meter. So again you have to put the pipes in the shaft. Again you do welding, then you have to do the RT, then coating, then it is inserted inside. So rugged rollers are connected with the installation of carrier pipes, and on the other end, receiving end, we have to put a winch machine to pull the carrier pipe inside the tunnel. Limited access to shaft. These are the challenges and limited access of shaft because of river water. It is flowing during monsoon, and during dry season also there are some flow of water which has been diverted using dams, and we face a lot of issues, local issues, because the water diverted is flowing to the villages. They have come with a request to stop all these activities, so we took the help of local administration. Thank you very much to the government of Assam and West Bengal for their support. Shipping of and delivery of the equipments and all accessories to a remote location like Kanamakra, Tista River is very difficult. Substantial time of insertion of carrier pipe, because you are cutting the pipes of the 1200 meter into 6 meter pieces. So insertion takes a lot of time. High cost as compared to conventional method of crossing. Its cost is almost 3.64 lakhs to 4 lakhs excluding GST. This is very huge. But
Only
in
one
case
and a half minutes left. Only 1.5 minutes left.
okay, so high cost is compared. Geotech survey is very important before commencing this type of activities. And last but not least, the benefits of microneedling, it creates minimum pollution. That is the advantage, and it is very accurate and precise, but at the same time costly. environmental sound technology, fast construction due to skilled and easy machinery, and suitable for congested areas. In city areas, this micro tunneling generally done by the metros, railways, but they are not doing in the river. But first time in the history of GAIL, we did the micro tunneling. And soil condition and geotechnical survey report is very important. Based on that, you have to select the drill site cutter, and it is very important. Thorough examination of conditional factors during design and execution, understanding significance of managerial, environment, physical factors, mobilization of resources and contingency planning influence the project timeline. This is very important. Thank you so much.
Thank you very much, Mr. Rajiv. It was a beautiful presentation, and the topic is so vast that if somebody is really interested, they can interact with the author later on. So, next speaker in this session is Dr. Ravikant Arya. He will speak about the role of elite metering and automation in gas reconciliation in CGD.
I thank you, Dr. D.V. Shastri. A warm good afternoon to all here present over here. So the topic of my presentation is role of elite metering and automation in gas reconciliation in city gas distribution. I'm having close to 24 years of experience in IGL, so would be sharing my journey in the segments of gas reconciliation and automation. As a typical CGD involves in distribution of natural gas to major four sectors: transport, industrial, commercial, and domestic segment. CGD ensures a reliable supply of clean and efficient energy through pipelines and CNG stations, promoting sustainability and energy efficiency. So as on date, IGL is having a presence in 11 geographical areas spread out in 4 states and union territories. Predominantly, IGL is having a presence in Delhi. In UP, we are having a presence in Gautam Nagar, Hapur, Shamli, Meerut, Muzaffarnagar, Fatehpur, Hamirpur, and Kanpur. In Haryana, we are having a presence in Rewari, Gurgaon, Karnal, and Kaithal. In Rajasthan, we are having a presence in Ajmer, Pali, and Rajsamand. So, a CGD business is divided into two major categories. One is CNG segment and PNG segment. As on date, we are catering from more than 850 CNG stations. We are catering to more than 20 lakh domestic PNG customers, and we are serving to more than 11,700 industrial and commercial connections. So gas reconciliation is basically a process of balancing the whatever gas which we take from the city gate station to the CGD entity, and balancing with the sale which we have done through CNG segment, through PNG segment, DPNG segment, industrial and commercial segment, plus the component of system usage gas, which is basically the internal consumption of gas being used in the gas engines, and also the gas being consumed in operation and maintenance of the machines. So internationally, the term is used as unaccounted gas. The term uses LUAG, loss on unaccounted for gas. So the idea, the focus is for the loss reduction of LUAG, and the prima facie the CGD works for the reduction of the LUAG component, and the main thing is identification of the leaks, whether it could be due to theft, whether it could be due to fugitive emissions, it could be due to metering inaccuracies. If we lower down this LUAG, then we will be controlling the financial losses to the company. Then the second area of focus is the metering accuracy. CGD should ensure precise metering as well as accurate metering, which is being done through various flow meters which have been installed. This will ensure accurate billing and better revenue generation to the company. Then the third area of focus is the automation of the processes. So if we broadly classify gas measurement, there are two basic principles. One is the mass flow measurement. It is being done through Coriolis mass flow meters as well as thermal mass flow meters. And volumetric flow metering is being done through positive displacement meter. Diaphragm meters and RPD meters are the positive displacement meters. And there's other classification of inferential based metering, which is done through turbine meters and ultrasonic meters. And CNG stations, we are predominantly using Coriolis based mass flow meters because they are highly precise, they have a better accuracy, They are immune to changes to gas composition, and there is no upstream and downstream requirement for the straight line connection. In PNG segment, we are using RPD, diaphragm turbine meters, and ultrasonic meters. So these are the various segments which a CGD has, and this is the evolution of metering methods which IGL has experienced, and most likely the CGDs would be benefiting from it. Considering the first segment as the CGS segment, initially few of the CGS stations were having orifice-based metering. Then it was having some problems pertaining to the maintenance and the accuracy class. They were upgraded to turbine meters in the middle 2005 to 10. Then now they have been upgraded to ultrasonic meters. This has improved the accuracy and the losses across for the CGD as well as for the CGS NTD. Then coming on to the second segment, it is the CNG station inlet. Initially, compressor suction flow meters were volumetric based, those were RPD meters. Then from 2004 and 5, they got changed into Corliss based metering. And IGL was the first company to use ALIT based metering. ALIT means you are having a better accuracy. It is like having accuracy of 0.25% to 0.3% vis-a-vis the normal Coriolis metering, which is having accuracy class of 0.5%. So as on date, if you want to improve down or have a better control on your losses, then you need to use ALIT phase metering. Initially, coming on to the next segment of engine inlet, initially there were no flow meters installed on the engine based compressor, and there was no method to draw a comparison or to check the efficiency of the engines. Then IGL installed the flow meters on the engine inlet, and in the new machines also we have taken with the engine inlet flow meter. With the help of that, we are able to gauge and compare the flow meter consumption across the engine packages, as well as monitor and control down the losses. Now then the next category comes of compressor discharge flow meter. In compressor discharge flow meter, if it is installed into your package, then user or O&M guy can easily identify where is the loss is happening, whether the loss is happening inside the compressor or it is happening post the discharge flow meter. So it is easily to identify, and he can immediately control the losses. In the FRS and INC segment, there were turbine-based meters initially being used, then they were upgraded to RPD meters, and now these days from the last few years, ultrasonic has made an entry and is giving good results. So these are the metering related challenges in the CGD network. There are diverse kind of meters which are installed in the CGD entity, right from beginning from the CGS to DPNG customers. The accuracy class also varies from plus minus 0.5% from the CGS to plus minus 6%, which is a DPNG customer. So maintaining a metering balance between all the flow meters and the number of flow meters installed, it poses a challenge, and CGD needs to take control over it. So there are other measurement accuracy challenges the CGD faces. One is the gas composition variability. As I earlier told you, like mass flow meters are immune to the gas flow composition, as well as the pressure and temperature effects, they are immune. But pressure, temperature, as well as gas composition has an impact on volumetric flow meter. So you need to install electronic volume corrector to have a corrected volume. And it is not possible for a CGD entity to install EVC for each and every segment. So they need to trade off based on the volume. And also CGD needs to identify whether the flow meter which is working in the low flow area or on the peak demand, that is whether it is working in the less than 10% of the 100% of the flow rate, or it is exceeding or working near to the 100% of the flow rate. So if it is maintained between those levels, you can have a better accuracy. Then maintenance and calibration, the CGD needs to devise a calibration policy based on the type of meters and based on the usage, based on the quality of gas, based on the contamination issues, based on the aging infrastructure. The calibration frequency needs to be devised and revised frequently. Then there is another challenge based on the theft, tampering, and unauthorized access, which poses a challenge. And for this, the CGD needs to have a surprise checks on it. It's a high volume customers. And coming on to the last challenge, that is the data integrity issue. As on date, new technology advancements have been taking place. So the data is flowing from your meter to your head-end system to the meter data management system, then to the ERP system for the billing. So data flows across various servers. So a data integrity challenge also poses a challenge. So these are the automation and advanced techniques which IGL have been using over the years. The SCADA has been implemented in CNG and PNG segment, which I will be showcasing in the coming slides. Then AMR has been implemented in prepaid smart meters have been using in domestic segment and the industrial and commercial segment. One of the specific tool which IGL have been very benefited is by using of laser methane detectors. From the last 3-4 years, we have been very efficiently using the laser methane detectors in all the cases, such as the steel pipeline monitoring, the underground wall chamber monitoring, the MDP pipeline monitoring, the risers, as well as the even inside the households. So it is a very handy tool. It quickly identifies the leakages, and a person can immediately act upon rectification of those leakages. Then at IGL, we are monitoring the daily bucket losses. We have classified the losses into 3 type of buckets, whether the loss is happening in the steel segment, it is happening in the MDP segment, or it is happening in the CNG segment. So based on the results, individual team can go and monitor this. Then data from all these segments is fed to an analytical system which provides a data-driven decisions. So this is the SCADA which is implemented in the PNG segment. All the steel pipeline network is having a network of sectionalizing walls. All these sectionalizing walls have been integrated with the SCADA system. In case of emergency, we can remotely operate these walls as well as like a traditional SCADA system. The logging of critical parameter, generation of alarms, trends, and everything can be done. The SCADA system has also been implemented in the CNG segment, as you can see on the topmost right side. User can pull over his mouse over a particular location of the CNG station in a geospatial view, and he can or she can immediately identify what is the suction pressure, what is the discharge pressure across the CNG station, what is the status of the equipment, whether the equipment is running, it is closed, or it is having a fault stage. And remote pricing change is occasionally being done once in a quarter. And there was a time when IGL did an incentivizing scheme for a few years, wherein daily and the night time the prices got reduced or got discounted by 1.5 rupees, and they automatically got reverted to its original price automatically in the morning without any manual intervention. So, and the other features are similar to a typical SCADA system, not going into the much detail. So all these data, whatever the automation which IGL has done from the IT and OT system, that comes to the landing page of a general service platform. This is a business analytical tool which IGL has developed. Herein, the 2 major departments, CNG, PNG, have been using it, and other support functions have also been using it from last few years. So these are the key functionalities of the general service platform. So it's basically an umbrella application where all the IT and OT applications merge, and the data is analyzed, and it is offering insight for fast and effective decisions. IGL monitors all these key performance indicators with the help of analytical dashboards. There are ready reckoner reports which are available with the user at every 9 a.m. in the morning, and it has reduced the analytical and the manual work, which is the repetitive kind of nature. Then there are analytical and insight reports which are shared in terms of automatic email to the user, so that he or she can take an action accordingly. So these are basically the outliers for which flags have been raised, and it gives an indication what is going wrong with the normal system. As GSP is sourcing the auditing the source data, so it is improving the data governance and the data literacy across the organization. In the last few years, we have rectified more than 3 lakh records in our SAP system, making the system robust. So it has been built on the lines of the organization hierarchical structure. There are different tier level dashboards based on the lower management, based on the middle management, and based on the top management. So some predictive use cases have also been built based on machine learning and artificial intelligence. In all, it is building a culture of analytics within IGL for data-driven decisions. This is a flash news which we normally circulate in IGL at the end of the financial year. Here you can see the rise in the adoption of GSP usage across the last few years. And as people have been using it more, the increase in number of dashboards showcases how the culture of analytics is getting increased in IGL. So, IGL won the Business Transformation Award from Tech Circle in 2003 for successful implementation of digital transformation tool for business analytics. Also, IGL has received appreciation from Climate Compass for negligible leakages. This is all which I have to say, and thanks you for patient listening.
Thank you, Dr. Arya. In fact, as all of us are aware, metering, accuracy of metering plays a very critical role in CGD business. So, next speaker is from South Asia Gas Enterprises, Mr. Ian Nash. He will talk about the uh, pipeline from Middle East to India.
Thank you, Mr. Shastri. Good afternoon, everybody. Hope you had a nice lunch. I'm going to talk about the technical challenges of a deep water energy transportation route to India. Peritus has been working with SAGE on a pipeline of this route for the last 15 years, but more recently we've also been working on what may be done in the way of a cable across the same route. Firstly, I'll start with just a little bit about ourselves. I'll then move on to the deep water route characteristics, then some general challenges of the route, some general challenges of pipelines, cables, and then draw some conclusions. Peritus was formed in 2010, and we're a global engineering services company to the energy industry. We work on subsea and floating systems and management services, and we are specialists in hostile, remote, and deep water environments. Here's some of our services, but specifically today we're looking at the pipelines and cables. So what do we mean by a deep water route? If we're trying to get from the Middle East to India, the deep water route could be from the UAE, which would be 1,600 kilometers long, with a maximum water depth of 3,450 meters, or from Oman, where the route length will be 1,200 kilometers long and the same maximum water depth of 3,450 meters. The reason it's the same depth is because the two routes would in fact join about 300 kilometers offshore Oman. So why is the depth important? The depth constraints. This map shows in pink water depths which are greater than 3,000 meters. And the significance of 3,000 meters is at this point in time, there are no cables, HVDC cables, which have been qualified to go deeper than 3,000 meters. So we can see there is no route from the Middle East to India that does not go less than 3,000, that goes less than 3,000 meters. If you want to follow a shallower route, there is a route that would be less than 3,000, but it's very close to the coasts of Iran and Pakistan. And the mid-water route, as I call it, which is less than 3,000, would be routed for many hundreds of kilometers through the Makran subduction zone, which is a very active plate tectonic boundary. The shallow route would be within the territorial waters and contiguous zone of Iran and Pakistan. Both of those two shallow routes will have to cross the Indus Canyon in the continental shelf just offshore Pakistan, which is a very, very significant feature. The deep water route has to cross the Owen fracture zone, which again is a tectonic plate boundary, and it also has to cross the Indus Fan channels at about 2,500 meters. So the depth is quite important. What does that look like in reality? So here we have a profile of the route from Oman to India, and you can see the shallow water on the Oman shelf is only about 40 kilometers long. And then we drop very quickly down to 2,500 meters, and then below 3,000 meters. And 3,000 meters again is the depth limit for qualified cables. So it's very significant. In the middle, we rise slightly as we cross the Murray Ridge features and the Owen fracture zone, which is where the plate boundary is. Then we drop to the deepest part of the route in the lower Indus Fan area, where we reach 3,450. And then we rise as we go over the middle Indus Fan, which is where the significant Indus Fan channels are. And there are 5 main channels to be crossed. and then slowly we rise up the Indian slope to a continental shelf in India, which is about 120 kilometers long.
Good afternoon, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed. Please take care of your belongings. Thank you.
Moving on then to the route challenges, not only depth, we have other challenging conditions, such as the metocean conditions, where we observe multiple directions of sea states, large sea states, and currents, which are not so problematic for the as-installed product, be it pipeline or cable, but they are important for the installation and the installation vessels that have to install these items. There are, going across the Arabian Sea, many other users of the sea. As you can see from the graphic in the middle, there are multiple telecommunications cables crossing this route. So a very significant number of crossings, and they are all in the very deep water. There is also oil and gas exploration. There are wrecks on the continental shelves, and there are in fact military zones on some of the shelf areas and slope areas. Lastly is geopolitics. When the work we first did on the pipeline was performed, we were going through the EEZ of Oman, international waters, and the EEZ of India. Now, since then, both Pakistan, Oman, and India have all made claims for an extended continental shelf, which is the area beyond the EEZ, and the pipeline in what was the international waters, or still is international waters, would actually pass through competing claim areas. So specific route challenges. There are steep slopes on the Oman slope and the Indian slope. These slopes can be up to 30 degrees, which for a pipeline is very significant, and indeed for a cable. These can cause difficulties to install and can cause difficulties to survey. There is seismic activity. I said we cross the Owen fracture zone. This here in the middle is a graphic from the reconnaissance survey that was performed in 2013 for the pipeline, where we're looking at the edge of the Dalrymple Trough. That's the deep area on the bottom right, which is 4,000 meters deep, and you can see the fracture zone crossing. This is deemed to be moving at about 7 millimeters per year, which may not seem very much, but it doesn't happen gradually. It happens in discrete events. So from the pipeline's perspective, we've looked at 1,000 years worth of movement occurring instantaneously. There are also potential for turbidity flow issues, and certainly these crossings have to be designed for. They can be designed, but they have to be designed. And then there are subsea canyons. I mentioned the Indus Fan canyons. Here again we see work from the reconnaissance survey of canyon number 4, which is about 300 meters deep, and the base of the canyon is only about 80 meters wide. So that can lead to quite long unsupported lengths and needs careful engineering. So looking first at specific pipeline challenges, can we design it? Can we? And the answer is yes, we can, and we have. And it can be designed in accordance with recognized international codes such as DNV STF 101. Can we make it? Yes, we can make it. In fact, SAGE has done a lot of work with pipe mills both in India and Europe and Japan on developing pipe for this pipeline. Can it be installed? Yes, there are vessels now with the capability to install this pipeline, and there are repair systems available. If we look on specific cable challenges, can we design it? Yes, there are design codes available to develop cables suitable for this deep water. Can we make it? The answer is almost certainly, but as yet no one has, and there requires quite an amount of assessment required and testing required, but the indications are from the major cable manufacturers that it could be made. Can we install it? Yes, there are vessels available to install this cable at these water depths. However, one of the key features of cables is they have a defined length, and that's to do with the carousels. And the carousels required are constrained to 10,000 ton limit. And that would mean that there would be multiple sections of this cable that would have to be joined as we were going along, which leads to issues of fatigue in the sense that these cables are deemed to be static, not dynamic. And whilst you're holding the cable with something like a 4-kilometer catenary of hanging cable off the back of a vessel, there could be a significant amount of fatigue induced during that joining process. So that needs to be looked at in some detail. And can it be repaired? Yes, the repair systems exist, although at this point none have been tested. So from an economics perspective, speed up now, we'll compare the two. It's not straightforward to compare the two. It's highly dependent on the business case, what you actually want to use the energy for. The gas has an advantage of being able to be used for feedstock as well as electrical generation and for city gas. Obviously, if you're just delivering electrons, it can only be used for electricity. If we look at the amount of cables required to match a single gas pipeline, you would need 4 pairs of cables to deliver the same amount of electrical energy in India as one gas pipeline can deliver. 4 pairs of cables would cost approximately twice as much as a single gas pipeline. I would highlight that these are very high-level assumptions we've made in doing this cost comparison. Quickly then, as a comparison, from a pipeline's perspective, the water depth is fine. Cable, nothing is currently certified at that water depth. Geohazards, the solutions have been found for pipelines. The solutions for cables, fault movement, etc., have to be analyzed. Seismic activity, both systems are fine. Installation vessels exist, although, again, a large number of joints for cables. From a schedule perspective, it's known with respect to delivery of pipelines. There's an uncertainty from a cable perspective because of the market capacity to deliver this amount of cables. Service life is about 50 years for a pipeline. Typically, service life for HVDC cables is about 25 years. Security of supply, well, if you've got one pipeline and it fails, you've only got a single point of failure. If you've got 4 cables, you can lose one and still have 3/4 of the supply. Project risk, the main risk is not doing enough engineering. From a pipeline perspective, if you do enough, the risks are fairly low. From a cable perspective, the biggest project risk is bottlenecks in the manufacture of cables. Now, I'll quickly touch on net zero. We talked about gas going, and that is not necessarily net zero, but if we look at what opportunities exist offshore India for carbon sequestration, we can see the bulk of the opportunities, the red dots, exist off the west coast of India. And if we tie that to what that means for a pipeline, we're providing gas into that west coast, very close to the potential sources of sequestration. So you can imagine a virtuous circle, as it were, of providing gas, generating electricity, but also providing cement works, steel mills, gas into the grid, collecting that CO2 from those sources, and developing CCS storage sites in the old Mumbai high fields. So quickly run through some conclusions. Energy transportation across the Arabian Sea is technically challenging. It is possible, but it needs significant engineering and investigations. The pipeline engineering is far more advanced for this route than the cable option. The choice between a pipeline delivering gas and a cable delivering electrons is very much dependent on the business case, what you intend to use the energy for. We've actually been working, as I say, both on the deep water pipeline and deep water cable with various players for some while. and there are opportunities that can be used to achieve net zero with reliable power generation by combining it with CCS in storage in local storage sites in offshore India.
Thank you very much, Mr. Ian Nash, for a nice presentation on Middle East to India deepwater pipeline. And I'm very happy that all the speakers are maintaining the time allotted to them. So next in the series is presentation by Mr. Manmohan Ahuja, who will be speaking on the issue of using ISO containers for LNG transportation, and he will share a case study. Over to you.
Thank you, Shastri ji. And prior to me, my co-speakers Rajiv, Ravi, and Ian have probably spoken very well on pipeline. And no doubt, the pipeline is definitely a more established way of energy transportation, and specifically when it comes to huge volumes. Well, I am going to come up with a very, uniquely different method, and that is probably for the consumers in the CGD industry, which are talking about sometime much lower volumes as compared to the industry and pipeline. So, and that would be basically, the mode of LNG. Uh, uh, so, just a little bit brief of my company. We are AG&P Pratham and Think Gas, and you would have probably come to know today the two companies have merged together and the new brand is launched and will be shortly known as Think Gas. And we are basically covering 10 states collectively, Think Gas and AG&P, and 49 districts and about roughly 10% of the India's area. We are in north as well as south of the country. And why this topic came to my mind and why I'm discussing and coming up with this case study is that we are, PNGRB and Government of India, they have come up with sudden expansion of CGD, whereby all geographical areas now in the country have allocated. But incidentally, the same is not been the pace of the development of the pipeline and providing CGS and connectivity to these GAs. And we in our southern GAs, which are in state of Karnataka, Andhra, and Tamil Nadu, we were having many GAs where we didn't have connectivity with the pipeline. So we had no option but to go for LNG route. And when we went for LNG route, we faced certain challenges, and that's the purpose of my topic today, and which I am bringing as a case to you, where LNG could be transported using the ISO containers as well. We as a company are backed by I Squared Capital, which is our principal investor, then Osaka Gas of Japan and Join as well as Sumitomo are our stakeholders. Uh, I think we have, this is a very quick snapshot. We have currently 15 LCNG stations, 19 CGS stations collectively, and we have 450 plus CNG stations currently collectively. With respect to LCNG, we have total of 24 LCNG stations as on date. In north of India, we have 3, 2 in Rajasthan and 1 in Madhya Pradesh. In south, we have 21. In state of Karnataka, we have 8, Tamil Nadu 3, Andhra Pradesh 5, and likewise in Kerala 5. Out of these 24, as on date, 15 are commissioned and 5 are under construction and 4 are at different stages of planning. I think I did mention why the need of LNG transportation by ISO container. Basically, we have to reach, likewise my co-speaker spoke, by pipeline and all those things, but eventually we have to still reach to the isolated consumers where still approach of pipeline is far away, and that's why we come up with this. This is just a description of the similarity between the two routes. One is through pipeline and another is through LNG mode, which is LNG by trucking, then LCNG station, and then going to the consumers. I'm just giving a very quick comparison. Sometime it's not that always pipeline network is very useful, but sometime this reaching individual consumers, whether it's domestic or gas, reaching through this business can be equally. For example, I have just done a very case study here, where a city area of around 50 by 50 kilometer, or we say to something like 2,500 square kilometers. If you cover the CNG stations to meet the demand of area, and approximately the nodes you need a station every 7.5 kilometer, for which you will need 36 CNG stations and a 300-kilometer pipeline network of CNG. Whereas you can probably do the same with 36 LCNG fill stations, again same, but just with the 5-6 LNG trailers. Indeed, for this you will have to bring LNG to that area, and how you bring this is the ISO containers can play a role in that. This broadly, I think I have spoken number of times in my previous slides, that what is the advantage of ISO containers. They can scale up the business anyway. You can do it inter-modal transfer, like you can bring it from outside country, you can do it within country, and they can make help LCNG stations more viable if certain flexibilities in the current regulations are allowed, which I'll speak to. Currently, as such, the code governing in the country with respect to these containers are SMPV rules, and PESO guidelines are primarily within the country are governing codes. Of course, internationally, it's American Society of Mechanical Engineers and Transportation of Hazardous Goods are the codes available for that. What essentially, I'm sure we are all familiar with ISO containers, but still I would say it is just basically like any LNG truck, but it is within a frame. It's a basically inlet in tank, which is made of SS304 or similar metallurgy, which can have the cryogenic product LNG stored at -160. Then it's super insulation, a vacuum plus perlite insulation, and then it's a framework which makes it easily transportable, so that you can put it on a flatbed truck, you can put it on a top deck of a ship, or you can put it on even a railway carrier. The beauty of the insulation and the design is it can sustain from 60 to 180 days without reaching the pressure which is resulting into safety valve popping. The insulation is such well done so that it can withstand the period of around shipments if you are doing across global trade, or if you are going from a particular place even by railway, then making it a hub. Even if you end up 60 days or 120 days, depending upon the design, depending upon the insulation, you can survive for that. This is a typical chain. If you bring ISO containers from exporting countries, or if you do it within the country, then you can truncate it to the lower half. Basically, it's from filling station, you transport it to the port. From ports, you load it into the ship. Generally, because they are hazardous good, they are done it on top deck. And then again, you come back ship, then at the receiving port, then from receiving port onto the container, and then going back to the LCNG stations. The case study which we did a case study of bringing for meeting our aspirations of LNG for our southern GS, and we did a case study on on the western coast, bringing it from any of the nearest sources, be it Qatar, be it Oman, and on the eastern coast we did it from the Malaysia. And the study concluded that if you need the quantities of the order of between zero point 0.1 to 0.15 million tons per annum, then probably it is more competitive than a large scale LNG shipping chain of the order of 5 million tons, etc., which is governed by the huge carriers. So that is if you are bringing it from a exporting country to the country, this country itself, until it reaches the last mile of our own LCNG stations. And another study which we did, and probably this would be contrary to the today's regulation, because today, although in SMPV rules as well as this PESO guidelines, we are allowed to have ISO containers, but they are not allowed to be separated from the prime mover, which means is that the ISO container and prime mover are wedded to each other, and and secondly, we cannot use, as per the rules today, these ISO containers as a temporary storage or even a parking. So that's the point. We had a recent discussion with Ministry of Petroleum and Natural Gas as well as PESO, as core ministry, which is Department of Industries, and we are trying for these rules to be revised to match with the international practices, where this ISO containers can be parked in a particular hub, and then it can serve a few LCNG stations. And then if this is allowed to be separated from the prime mover, it can result into space saving also for LCNG station, which is the biggest challenge today the country is facing and the CGD companies are facing, because within a city we need, if we need to establish a LCNG station, we need substantially large space, which is a rare commodity, I will say today. I did a case here, for example, if a station is selling around 10,000 SCMD, then how much, if you are not allowed to separate, if you go for conventional storage, like a 56 KL tank, and then from there you are vaporizing and feeding as a CNG, you need around 1200 square meters of area. On the contrary, if the rules are revised and they meet as per the international guidelines, where it is again ISO containers are used for parking and temporary storage and hub, which is the primarily purpose in fact of the ISO containers, then probably we can come down to a very substantial low saving, which is 650 square meters I have done, which is practically half of it. See, this is what we wanted to propose, and we want to say, like these ISO containers, if you have a within a a circle where you have a few LCNG stations and you want to feed them, you have a very small storage vessel there, maybe around only 10 metric cube or 12 metric cube, and then you, as the need basis, you move ISO container from this hub to that LCNG station. Thereby, within the LCNG station, storage space is very limited. Then based on the distance requirements of inter-equipment distance requirement today, as stipulated in the rule, you can do in a very lesser space, and you can save substantially on this prime mover cost, which is the major cost in the LNG transportation for LCNG stations. This is just, I want to show how you could reduce the area with this was one needed around 1100 square meters when you go for a bigger storage tank, and if you go for a smaller storage tank and use ISO containers, you come down to half of it. This just in order to say today in the country, a regulatory framework I mentioned, it's PESO, it's SMPV rules, and internationally we have mentioned that, and that's all I wanted to say. Thanks.
Thank you very much, Mr. Ahuja, for the concise and precise presentation. And now, last but not the least important, rather most important presentation is coming from Mr. Mohit Bhatia, Director Commercial, Indraprastha Gas Limited, who will discuss about the topic of natural gas and LNG processing, operations and technology. Over to Mr. Bhatia.
Good afternoon, all. Thank you, Mr. Shastri. It's a great thing to be here with such a wonderful audience. Just to start the topic for me, I am going to present on small scale liquefied natural gas, that is the mini LPG plants, mini LNG plants. So first of all, we need to understand the context. See, India aspires to take its natural gas contribution in the energy basket from 6% to 15% by 2030, right? So it can happen definitely, but it cannot happen without the LNG coming into a big picture. So, as you know, I just wanted to share some statistics with you. See, presently, India is consuming almost 90 million tons of diesel per annum throughout the country, and 10% of this is coming from long distance hauling of the intrastate as well as interstate truck movements. So if we could convert 10 to 15%, that comes to almost 9 to 15 million tons of LNG business potential we have. Secondly, there is an urgent need to develop the ecosystem. See, we have all the ports of LNG terminals either in the west coast or east coast, but commuting or bringing the LNG from the coastal areas to the hinterland, it is more than, particularly northern part of the country, it is more than almost 1500 kilometers, and there is a boil of gas issues and all. So entire ecosystem, if it has to be developed, then the picture comes of the small scale LNG. And good thing is government is also planning to give a domestic allocation of 5 million per day on the LNG thing also. So this is the basically context which I wanted to set in before going into the presentation. So why there is a need of small scale liquefied natural gas plants. So I'll be covering the contents in primarily global and India energy scenario, small scale introduction. I have given some overview to you. What are the SSLNG technologies available across the world, and how we can encash particularly for the CGD sector through CNG. So this is the just the global and India energy scenario. So across the globe, around 14,000 plus of oil equivalent, million tons of oil equivalent, the consumption is there, and out of which natural gas is contributing to around 23%. Whereas if we see the India pie, it is around 900 plus 929 million tons of oil equivalent, whereas we are now at around 6%. So across the world also there is a global demand, and from the current level of 4,800 BCM, it is expected to grow. It is expected to grow from 4,200 to 4,800 BCM by 2040. Friends, if we just see the global energy market, we need to also understand where India stands. We all know that it is the third largest energy consumer for oil. We are also the fourth largest LNG importer, and also the third largest LPG consumer, as well as the fourth largest refinery with a capacity of around 250 million tons per annum. And also, India is having a market of almost fourth largest automobile market within the country. So just coming on the applicability. So why and where it is applicable, this particularly small scale LNG. See, we can have a seamless integration with any of our existing CNG stations across the country, having natural pipeline connectivity the CNG stations, and it can be converted into LNG and then can be taken further. Similarly, as I already mentioned earlier also, it can be used as a hub and spoke model. We can take the LNG generated through the SS LNG plants and take it to the mountainous areas, and then from there the CNG can be transported to further areas. Thirdly, wherever there are wells where the production capacity is less and laying of pipeline and capex is a heavy thing, then the consumers with intermediate or irregular requirements, there also this thing is highly applicable. And if we see, if we want to set up the entire ecosystem, so instead of going for a huge pipeline infrastructure, it can be it can be taken into the small scale LNG part because it is movable and scalable also. And then we can also utilize to build anchor demand within the pipelines where it is in the development phase, the pipelines. SSLNG is being not a new thing, it is being used and it is being now established across the globe, across the continents, across various countries. In India also, GAIL India has already established and it is there in Vijapur. And now the things are coming up, shaping up, and at IGL level also we are planning for this to take it forward. So there are a lot of technologies for developing the small scale LNG, but primarily just to share with all of you, I'll be talking on three of the technologies. See, based on Stirling cycle, wherein an external a cooling refrigerant is taken, for example, helium, and it is taken as a coolant, and continuous expansion and compression of the helium is done through the external arrangement, and the cooling and the liquefaction things happen. Secondly, based on the Joule-Thomson effect, as you know, that whenever it is throttled after chilling and all, the gas gets liquefied and some portion can be taken to the LNG part and the VOG gases can be recycled and can be continuously chilled and further liquefaction happens. Thirdly, as we have the compressed gas also available across our CNG stations, and one part is already done, some cost benefit and cost economics is also there. And through further refrigeration and heat exchangers and all, it can be cooled down, and further through the Joule-Thomson effect, JT effect, it can be converted into LNG. So, not going into much into the nitty-gritties and all. So, this is one of the Stirling cycle process wherein the helium is at initially at the room temperature and then it is compressed from one stage to another stage, and the cooling thing happens, reducing the gas temperature, and further final cooling happens when it is further expanded. Secondly, we have the Joule-Thomson effect also, like when we have the treated PNG free from moisture and CO2 and all, then after the chiller effect, it is passed through the JT wall, giving a Joule-Thomson effect. And further, the refrigerant cycle is also there, like in this case, nitrogen cycle is there, which continuously recirculating the nitrogen, and finally the outcome is the cryo effect is there around 160 minus 160 degrees centigrade, and we get the LNG part, and some part of the VOG gases is recycled, and it will keep on recycling, and the LNG thing is produced. From CNG also, it is a good thing. It is already in India now also. See, from natural gas, when we get the compressed gas through the compressor stage and all, it can be used as CNG for storage and further dispensing through the CNG dispenser. And the other part is using this SSLNG plant with the refrigeration cycle. Basically, after the compression, you get the cooling heat exchangers and passing through the expanders either through JT effect and all, it can be converted into LNG and then further can be transported through hinterland, small places where the pipeline connectivity is not there, and it can be taken like that to the customer's end. This is a typical diagram how we can get it converted, in particularly after the compression stage, the various heat exchanger 1, 2 passes, and the temperature also goes down, and further through the JT effect from 220 particularly bars, it gets reduced to 4 bar, and the cryo effect also happens 160 degree minus P, and then the thing is converted, and it is further uh, can be liquefied. It is liquefied to the stage, and the VOG is again recycled and taken back. So these are some of the technologies. But now the good thing is like 1/3 of the CNG gets converted into LNG. The 2/3 quantity gets returned at low pressure, where multiple options are there. It can be fed as the low pressure into the MDP network. Also, it can be recirculated at the low pressure to the SSLNG plant and further added through the booster compressor. Then the optimum utilization of existing the CNG stations can happen, and the infrastructure and even the HR, manpower, AMC things can be also looked into for further reduction. Just coming on to the cost economics, it may not be sacrosanct, but just a working. See, the basically the equipment cost, the capex may happen to around 2 to 3 rupees per kg, but the energy thing, if we take on the renewable part, it is around 4 rupees per kg. If it is not on the renewable part, it may vary from 8 rupees to even on the 13-14 rupees also. And then the O&M cost, if you add, and ultimately it comes to around 10 to 15 rupees in case of SSLNG. Whereas if you transport up to 1200 kilometers, it works out to be around 10 to 11. But this is more beneficial when you have to transport the LNG beyond 200, beyond 1200, beyond 1300, beyond 1500 kilometers. Then it gives you an cutting edge. Then it gives you a upper edge. So this was on the cost economics, and further I also mentioned that it is more useful if we have around 1200 kilometers plus. So this system is more effective, and the conclusion is like SSLNG becomes more competitive compared to LNG trucking, depending on the plant utilization and customers prominently. While SSLNG requires significant capex, no doubt, it provides a long-term cost saving and reliability for remote and decentralized consumption centers. So with this, I close, and let's see how we take it forward. IGL is working on that. Thank you so much.
Thank you very much, Mr. Bhatia. And let me openly admit that this is perhaps one of the sessions which I have seen in 40 years of my career, that each of the speakers has concluded the presentation on time. So kudos to each one of you. And the topics are really interesting. We heard Mr. Rajiv Ek about crossing of 4 rivers by using micro-tunneling technique. Mr. Ravikant Arya about elite metering and gas reconciliation. Mr. Ian Nash about Middle East to India deep water pipeline, to use of ISO containers for transportation of LNG, and finally the small scale LNG. All areas are very promising, and as I said earlier also, if any one of you is interested in having some question answer or further deliberation, you are welcome to interact with them on phone or email. With this, I thank each of the speakers and the wonderful audience. Thank you very much.